Now we'll delve deeper into what probability is and how to quantify all these things. I said that probability is basically the framework or the measure by which we capture this uncertainty. Okay, we try to quantify the uncertainty. Now we'll first like to introduce some basic terms, and then on these basic terms we'll like to build the further mathematics which will be used in probability. The first thing I'd like to tell you is an experiment. What is an experiment? Okay, if you see what is an experiment basically means, we have been talking in the previous session that everything in the world mostly is probabilistic. Like if you see most of the things in the world, they're probabilistic. Okay, there is an uncertainty associated with them. So what experiment is? Experiment is if there is some randomness with it, there is some randomness associated, or there are a lot of features to capture. Okay, there are a lot of things that you wanted to capture that you cannot even count. There is something, some feature, some knowledge which is unknown to us. Okay, there is inherent randomness to it. That's the thing. And now the second thing that an experiment should have, it should have finite, or we can say well defined, rather I'll say well defined outputs. If these two things are there, I can call it an experiment. Okay, I can call it a probabilistic or random experiment. So experiment, there is some randomness involved in it, and it has some well defined output. Something will happen and that is well defined. Let's suppose, what an example. So the first example I'd say, if if let's suppose 7 horses are running in a race. So 7 horses are competing in a race. So now the question is, which horse will get what position? So there are 7 positions possible: 1, 2, 3, 4, 5, 6, 7. Now you saw that we don't know which horse will win. That we don't know which horse will come at what position, because there is some randomness associated with this. But the output is well defined. If you see, we know that there will be only 7 positions. Okay, 1, 2, 3, 4, 5, 6, 7. These are the positions. Okay, but we don't know what position, which horse will get what position. Second thing, which, like example which you always have been hearing, coin toss. So if you toss a coin, okay, toss a coin, so there is a randomness associated with it, because you don't know all the factors that affect its output. The thing that can be, it can be heads or tails. Okay, so these are the two outcomes possible, two outputs possible after you perform the experiment. If you roll a die, okay, so the possible outcomes are 1, 2, 3, 4, 5, 6, something like this. So there is randomness associated with it, and the output is sort of well defined output is there. So when something happens and we can quantify it, this is called an experiment. Okay, now going from the experiment, we'll go to the sample space and events. So we'll discuss what a sample space is. Sample space. Okay, so sample space is the set of all possible outcomes. In nutshell, I'll say the set of all possible outcomes of an experiment is known as sample space. I'll write it here. Set of all possible outcomes is called as sample space. Okay, so in for example the experiment that we did previously, these 7 horses are competing in a race, so this is the sample space. So this whole, because there are only these many possibilities, this is the sample space. Tossing a coin, this is the sample space. Rolling a die, this is the sample space. And if you toss 2 coins, so what are the possibilities? So when you toss 2 coins, so tossing 2 coins, this is the experiment. So what's the possible outcome? All possible outcomes: head will be there, okay, head tail will be there, tail head can be there, and tail can be there. So these are all possible outcomes that are possible in when you toss 2 coins. So this is called a sample space. Okay, now it's up to you how you construct sample space. You can construct sample space differently. Let's take an example again of tossing a coin. Tossing a coin, so you know that the possible outcomes of a coin can be head or tail. But what if there is some theory which says that toss of the coin and the weather is related? So there is some relation between coin, tossing of a coin and a weather. So you can say it can rain or it cannot rain, so no rain. So I am like, there is some theory, let's consider there is some theory which says tossing of a coin and weather has some relation with each other. So you can say, oh, if they have a relation, then probably that the outcome possible, if it is head, it can rain, head and rain, or head and no rain. Okay, then tail and rain, tail and no rain. This is now a sample space for you. Okay, and when you toss a coin and you are checking, oh, there, if there is some correlation, but you know that there obviously is not, that's why you write head comma tail, but this is also possible. Okay, now it depends on you, how do you even choose to define a sample space. So the first thing is based on some theory or something. If there is correlation between things, you may include some things in your sample space, and you may say this is nearly impossible, so I don't need to include this in sample space, or something like this. So this even can be changed. So even what you said is tossing of coin, you said sample space is head tail, tail head, and tail tail. You can say the sample space is how many heads do we get. So here you get two heads, here you get one head, here also you get one head, and here you get zero head. So this is also a sample space. Now you change the thing. So how to construct sample space depends on you, how to construct a sample space. So experiment, you understood. Sample space is the number of possible outcomes. So I said tossing two coins, two coins. So you can construct sample space. The one thing is you can say it can be head and head, it can be head tail, tail head, tail tail. So second thing I said, this is the face it appear, the faces. So what face will appear on the coin. So the second thing is how many number of heads are there, how many number of heads. This also can be a sample space. Okay, if you toss two coins, you are saying, okay, how many number of heads are there. So the possible outcome is 0, 1, and 2. This is the sample space for this experiment is same, but you just are asking me different question now. So based on the question, you are you are changing the sample space. Or even sometimes you can have the same question and you can have different sample spaces. Okay, but I hope that you understood the concept of sample spaces. Can I assume this you understood the concept of sample spaces?
Yes, sir.
So you can consider the sample space by
Yes,
yourself, and the thing is, you'll have to see what is the question that I'm answering about. Experiment is something which has random associated with it, and which has some well-defined outputs, and all the possible combination of outputs or the outcomes possible is called a sample space. Then we have something called as an experiment, something called as an event. Sorry, so event. So something can happen out of these. So either there can be head head, head tail, tail head, and tail tail. So any subset of sample space is called as an event. Okay. So if you ask me what is an event, so event basically is, so any subset of the sample space, all the possible outcomes is an event. So event is any subset, any subset of sample space. Sample space is all possible outcomes. Now in the head tail, if you ask me, what is an event, so I'll say an event can be this head can be one event, or even event can be phi. Phi means no event, nothing is happening. Okay, no experiment. So this phi is also a subset of the whole sample space. So I can say how many time how many so let's suppose taking this example of head, I can say how many outcomes are possible where there is at least one times a head is there. So this is head head, head tail, tail head. Okay, these are the outcomes possible where a head is there. This becomes an event. Okay, event is basically computation of heads or something like that. Is it clear? This is an
yes,
event.
sir.
So these are the important things that you have to know about the things. First is experiment, then what is the sample space, and what is an event. Now, before understanding anything about the probability, I'd first like to revise some set theoretic concepts. I'll introduce set theory because this is heavily used. So I'll introduce some concept from set theory, I think in couple of minutes, so that you understand most of these things from sets, and then we can resume our discussion on the probability. So let me introduce, you know what is a set. So obviously set is a well-defined set of objects. So set is well-defined collection of objects. Let's suppose if you have 1 comma 2 comma 3 comma 4, this is a set of integers which are positive and are less than 5. So this is a well-defined set. Okay, and then you might have heard there can be subsets. So subset means subset. So I'll just subset is has this notation. So if I write a is equal to 1 comma 2, so let's call this set as S. So I'll say A is a subset of S. Okay, and there is concept of superset. Superset is reverse. I can say S is a superset of A. Superset has this symbol. Okay, and then there is a concept of union. So what is the meaning of union? So if I have this A is equal to, some A dash is equal to 1 comma 2, some B dash is another set which is 5 6 7 8, something like this. So if I write A dash union B dash, so I have to combine all these elements. So I'll write it 1 comma 2 comma 5 6 7 8. So if there is some repetition, we don't include repetitions, we'll just include it once. Okay, this is called as union. Then there is intersection. So intersection is having the symbol this. So intersection means what is in the both sets. Okay, let's suppose we have a set A that's equal to 1 comma 2 comma 3 comma 4. Then we have a set B which is 3 5 6 4, something like this. So if I write A intersection B, it means what is common in both the sets. The common here, if you see, is this 2, not this 2, 3 and 4, I guess 3 and 4. So you can write intersection is 3 comma 4. Okay, union, intersection. Then an important concept that I will introduce is called as Venn diagram. So what is this? So this is a diagram representation of all these unions. What are the operations I showed you? So if I make something like this, so this is called as universal set. So what basically captures everything? This is an universal set. Let's suppose set of all numbers, so all real numbers. It's a universal set for numbers like integers, for some numbers like positive numbers, natural numbers, negative numbers, and things like that. So if I have a set, let's call this set, this is represented like this. Okay, and if some set is like this again, okay, this is our set S, this can be A and B. Okay, this A is a subset of S. Okay, B is also a subset of S, but A and B, as their intersection is phi, these are called disjoint sets. So this is called as disjoint sets. Disjoint means they have nothing in common. Okay, so this portion is of the A and this portion is of the B, and whatever is not in the B, whatever is not in the B, this portion including this A, this is called as B complement. Okay, B complement means B take everything in the B, take everything in the B, let's suppose take everything in the S except for this. So you can write take everything in the S and just remove this component from it, remove the other, and you can even write it in some other fashion also. So you can write B other than, let's suppose, S. So you remove the S part, whatever, and just keep the B in that. So that's called as B complement. This you can write it like this. This is the Venn diagram which I'm showing you. Even you can write A complement. A complement means this is A. What is outside A is called as A complement. Okay, and this diagram over here is called Venn diagram. Now I'll again show you this Venn diagram for, let's suppose we have two events A and B. I'll show you this intersection first. What is intersection? What is union also in the same diagram? So this is our S, a universal set which contains everything. So if we have an event A, if this intersection is not phi, so let's suppose if they intersect somewhere. Okay, so this is the intersection part. So this part. So I'll say A intersection B. This is only A. Okay, this is only A. If you remove B from the A, okay, if you remove, this is this symbol I said is remove. Remove A, B from the A. This is only A, and this is remove. Let's suppose this is A and this is B. Remove A from the B. This is only B. Okay, and this is our S. So union basically means this much. So union over here is this. So this over here is union. This is A union B. Is it clear? And if I have to again write a subset, if something is a subset of something, so what I'll write is, if this is our A, let's suppose A, and if this is our B, this is our B. So we'll write A is a superset of B, or B is a subset of A, because it's inside it, and these are all Venn diagrams. So again, to show you the complement, so maybe I'll write it here. So this is our universal set, and let's suppose this is a set A. If this is a set A, and over here whatever is there outside this A is called as A complement. And now you have the laws, obviously. So if you have A union B, that's obviously equal to B union A. Okay, if you have, let's suppose, A union B union C, so this is associative. So you can put the braces over here, or if it's A union B union C, you can first club these two things. You can clearly see it from the diagram. Okay, and there is distributive law also. So distributive law is A union B intersection C. Okay, if I write intersection C like this, so this is equal to A intersection C union A B intersection C. This is called as distributive law. Is it clear? You can check it with the check it with like three sets. Let's suppose we have a set A, we have a set B like this, and we have a set B, we have a set C. Okay, so this portion over here, which is common in all the all of these, this is called as A intersection B intersection C. This is intersection of all the sets. This portion, A intersection B intersection C. I hope that this, at least this was a quick revision of the set theory, because I'll be using these symbols and the Venn diagrams for rest of the discussion of the probability. That's why I wanted you to know all of this, all the symbols and these things. Now we'll start with the axioms of probability. Axioms of probability. Okay. So there are some certain axioms which are the proper axioms, which basically they don't have proof. They are something like intuitive, and something that are like true. We don't have proof for them. Okay, and now we want to quantify these things. I said, what is probability? It tries to give a metric. It tries to quantify what is uncertain, and gives some numbers to uncertainty. So what is the first axiom? The first axiom. These axioms were given by Kolmogorov. So I don't want you to go into that. There is a advanced probability course as well. They'll teach you something called a sigma algebra and things like that. But I think first the basics should be done, and afterwards you can go into advanced probability also. That's why even this probability was not built for a specific field. It was just a mathematical theory. And now you might have heard probability for machine learning, probability for physics, probability for like something else, and probability for biology is also there. Okay, and this probability was used in different fields then. And now the Kolmogorov was the one who mathematically molded and who put these three rules. The first rule of this is, so we have an event, let's suppose E, and we write probability of E like this. This is read as probability of E. This is the event E. This is an event. Event is a subset of an outcome, or subset of a sample space of all the possible outcomes. So we write this as probability of E. The first axiom is that probability of an event is between 0 and 1. Okay, this is the probability of an event. This is the first axiom. So if you have an event, so you have to assign a probability between 0 to 1. Okay, it cannot greater than 0. Somehow 0 means this event is not possible, and 1 event means it is certain. Okay, let's suppose we have all the events, so the sample space has a probability 1. Okay, this is the second axiom. Probability of whole sample space, that's equal to 1. This is the second axiom of the probability. The first axiom says that when you assign probability to any event, it should be between 0 and 1. 0 means, let's suppose, I hesitate to write it not possible, but for now you just remember it is not possible. But I'll show you events where probability 0 does not always mean not possible, and probability 1 doesn't mean always it is a certain event. Have you heard about this? Probability 0 does not mean not possible. It is mathematically like 0 probability means it won't occur. But I'll show you some examples where we'll show that probability 0 does not always mean not possible. And the second axiom says that if you have the sample space, the whole sample, the whole possible outcomes, the probability of whole sample space is 1. Let's suppose sample space S in terms of tossing one coin, we have sample space head or tail. So we are saying what is the possibility either head will come or tail will come, guaranteed one. So it's 1. Okay, because sample space is head or 0 for all sample space, the probability is 1. So even if you say probability of getting a head, we write it like this. So it is 1 by 2, let's suppose. So 1 by 2, we gave it a number between the 0 and 1. It cannot be, let's suppose, 3. This is wrong. We cannot assign probabilities like this. That's why these axioms are there. The first axiom is probability of an event should be between 0 and 1, and both inclusive. And probability of a sample space, probability of the whole sample space is equal to 1. And the third axiom is that if we have disjoint events, so what I mean by disjoint events, so they don't have anything in common. These are disjoint events. Okay, if this is our whole sample space, let's suppose this is our whole sample space, this is our sample space S, and this is event 1, event 2, event 3. Okay, if they are disjoint, there is no common element, nothing common in them. So we say that probability of union of all of these events, probability of union of these events, let's suppose event I is equal to probability of event 1 plus probability of event 2, and so on. Okay, for two events we'll say that probability of E1 union E2 is equal to probability of E1 plus probability of E2. But the condition is they should be disjoint. These are the only three events, these are the only three axioms that are with the probability. You can now conclude some other results from these, but these are the only three axioms of probability. Okay, and you know that like probability of phi, nothing occurring, what should be the probability of phi? These are the axioms. I'd write them right there. So this is the first axiom, axiom number 1, axiom number 2, and this is the axiom number 3. Okay, and now I'd ask you some questions and we'll prove them properly. Phi basically means the empty event in which there is nothing. So what is the probability of phi? What do you say intuitively? What should be the probability of phi? Any answers? Probability of nothing happening.
Yeah.
Waiting for the answer. I won't teach till. So probability of phi is 0. Like this is the intuitive idea, and we can even derive this from the three axioms that we just wrote. And even again, the thing is, if we have a event, let's suppose A, probability of A is the probability of A event happening. Probability of A complement. Okay, intuitively it will be 1 minus probability of A. We'll derive all of these. Okay, so these are some properties which you can even derive. Maybe you can derive it as a homework. It's really easy. You just have to use like maybe this and this to come up with this. The probability of phi is 0 and probability of A complement is equal to 1 minus probability of A, something like that. Okay, and there are some other properties that you would derive. This is your homework. Please do it. Otherwise, like in the next session, I'll ask you have you derived it. And we have still got some time. I'm just drinking some water. So now we'll take the first example where we'll first model the problem probability wise. Let's suppose you are doing an experiment and now you'll have to construct a sample space, and I'll get you into the thinking of how to construct a sample space. If there is an experiment or there is something happening, how to bring it in the probability model, and how to make a model in that. Okay, there are some experiments which are sequential in order, which are sequential in nature. Let's suppose you are tossing two dice. Okay, you are tossing two dice. A dice is that thing that you might have even seen. This is like this. It has six faces. Okay, and 1 2 3 4 5 and 6. Okay, this is the dice which we roll, and we want to model an experiment like this. So these are called as sequential models. So if you are rolling two dice, these are called as sequential models, because some models are inherently sequential. So you perform one thing, after that you perform another thing. Okay, and this is sequential model. So if you have a die which has six faces, so what is the sample space in that? So sample space for each die, if you see it, the outcomes possible for each die S1 and S2, this is 1 2 3 4 5 and 6, and same for this. So now see how like sort of quantify this. I'm taking a very simple example. When we take more complex examples, there you should be able to know how to make a sample space. Okay, if you have to have a bigger, let's suppose larger sample size, and there, and what to do in those aspects. So the first way how to make these is, and how to assign this probability, which the diagram that we'll be frequently using to compute probabilities is, because when you roll one die, you can get any of these, or you can, and after you roll second die, you can get any other 1 2 3 4 5 6. So the first method I'll say, so that's called as box method. I'll name it box method. So how to compute the sample space and how to visually show it. So it's something like this. Okay, so here we'll capture what happened in the first die, the first roll, or rolling two dice simultaneously, or rolling one die After that, rolling the same die second time is the same experiment. This is the first roll, and here we have the second roll. Okay, so here you know that the 6 possibilities are possible, so we'll have 6 columns in that, because first row will have 6 possibilities. So 1, 2, 3, 4, 5 and 6. Here again we'll have 6 for the second row. 1, 2, 3, 4, 5 and 6. Okay, I write numbers here: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. This is our sample space now. Okay, this is one of the graphical method. So if I say why is 6 6 6 6 is here, okay, whereas let's suppose 4 5, so 4 5 will be somewhere like here, 4 and 5 it will be like here. Okay, first die is 4 and second die is 5, so 4 5 will be here. Now this is our whole sample space. If I say you where are these how many possibilities are there when the sum of the numbers is even. Sum of the numbers is even is 1 plus 1 is 2 right here. Okay, and then this is not there, and this 2 plus 2 is 4, this is there. Okay, then 2 plus 4 is 6, this cell is also there, and then again 2 plus 6, this is also there, like basically even. If you see 2 and 4 and 6, and if you have odd numbers, then you will have the odd entries 1, 3 and 5. The same thing with this 3, with 3 you will have 1, 3 and 5. For the 4 you will have 2, the even numbers basically 2. And if you see, basically they are diagonal elements. There's a pattern in here, that's what I wanted to show you. There's a pattern. Now it becomes really difficult to create a diagonal. This is the diagonal, I hope. Okay, so for 5 we have these two, and you see, if you sort of color these cells. Okay, I don't know if I have colored it right. All the cells that are colored are the cells where you get the sum of outputs that we go on 2 dice is even. So if you just have to now calculate probability by frequentist approach, so if somebody says probability of the probability of sum of digits is even, basically I'm speaking in terms of this die is even. So what is the total cells? How many cells are there? 36. And how many are these cells? 1 2 1 2 3 4 1 2 3 4 5 6 6 4 10, and 10 to 12. 12 4 is 16, I think 18. Half of the output, something like this. You can check the calculation. This is one of the methods. Just to show it where we use it, I'm just showing very simple examples. I'll be using it in a more complicated manner. So this is the first box method, where you create a box, and if you have this sequential experiment. Okay, and the other method is called as sequential tree method, or sequential tree description. Sequential tree. So how to write that? You will have a root, okay, where you will start experiment. Now you will have 6 possibilities. You have 6 possibilities: 1, 2, 3, 4, 5 and 6. Okay, for each of these possibilities you will again have 6 possibilities for the second roll. Okay, 1, 2, 3, 4, 5 and 6. Same for here, these. Okay, and then this is 1, 1, 2, 3, 4, 5 and 6. This is 1 2 3 4 5 and 6, and these are called leaves. So here this will be termed as 1 1, this is 1 2, this is 1 3, this is 1 4, this is as 1 5, this is 1 6. This is called as tree based model, and similar with these are called leaves. We'll call it leaf, one leaf. Is it clear? These are the two sort of pictorial representations by which, if there is a sequential model, you can make these pictures and then compute the probabilities. Okay, okay, now moving on. So there are discrete models and continuous models. What is a discrete model? So discrete model basically says, if the sample space, so discrete probability model or the models when the sample space is having discrete elements, so it has discrete values. Discrete values. So what's the meaning of discrete values? For example, if you take coin toss, so what in the coin toss we have heads or tails, heads, tails. These are discrete events. Okay, So how many subsets are possible? What is the event can be? It can be head, it can be tail. These are events. Let's suppose this is E1, event 1. These are event 2. Event 2 can be only tails. Event 3 can be heads or tails, the whole of this. Or event 4 can be nothing. We'll have 5. Event 4 can be 5. If events are discrete, okay, we can call them as discrete models. Like till the start, whatever the models we saw mostly were discrete models. Okay, if you now toss 3 coins, what is the possibility? So we can have head, 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 and head, tail, head, something like this, till tail, tail, tail. Okay, these are all discrete, and subset of these is also discrete, and these are discrete models. And then we have continuous models. Continuous, you must know all of these basics, so as when you compute the probability, or when we'll use uh, uh, advanced examples and things like that, there we'll use these basic concepts. What is the continuous model? So which have continuous sample space. They have continuous sample space. Okay, so discrete has the discrete values, for example, we saw in the coin toss, and but these things, they have continuous sample space. Let's suppose if you are writing a sample, say let's suppose this game you might have played. So if you throw these arrows or have a dot you want to play, okay, and here it can land anywhere. This dot can be here, here, anywhere. There are infinite number of points. Okay, so if you play that game of throwing the dots, okay, on that board, that board is circular. So where does the dot land? Okay, let's suppose this experiment is throwing a dot. It is a random experiment. Then the sample space would be wherever you throw the dot, that is one of the outputs of, or one of the outcomes of the experiment, and you know that these outcomes are continuous. So it can, for example, if you have these quadrants, it can let's suppose we have not this, we have a circular board like this, something like this. Let's suppose it starts with 0 1, and here we have 1 also. Okay, so x-axis value will be less than 1, greater than 0. Again, y-axis values will be, so we'll have a pair of outcomes. So wherever you land, let's suppose your dot landed at this point. Okay, so it will have an x coordinate, it will have a y coordinate over here. So outcomes will be like this. So sample space will be x comma y, such that x is from 0 to 1, comma y is also from 0 to 1. Now you saw that this sample space is continuous. It can take values of 1.1 comma 1.2 for one value. Let's suppose that's over here, not even 1.1, sorry. It can take value 0.5, 0.6. That's, let's suppose, here, some value over here. It can take the value right there, 0.00, 0.5, 0001, comma 0.6001, something like that. That's just above it. Okay, but the sample space, if you see it, it is continuous. Is it clear?
Yes, sir.
Okay,
Yes, sir.
so these are the models. Like then if you have this sort of knowledge, then we'll do some examples in the next session, and then we'll move on to the conditional probability. I think this is the enough theory that you require to solve some problems of probability which are introductory in nature. And please, one more suggestion I'll give you here is, because I could not cover everything, so cover a topic which is known as combinatorics, where you have these permutations and combinations, because that's also heavily used in probability, because we have to count a lot of things. You count what is the number of events in which this happened, or number of outcomes in which this happened. So you'll have to count a lot. So there you will, these things will come handy, permutations and combinations. Watch some lectures, watch some remember some formulas in there, because I'll be referring heavily to this when we introduce some probability problems, and then you'll have to count something. This is also your homework. One homework I gave you to prove some properties like this based on the axioms that we had. So we had some axioms, and then these are some of the things, which is your first homework. Please prove this. And the second homework that I'm telling you is, please go through this permutations and combinations. Next time we'll go into the conditional probability, and then we'll also go to what is like marginal probability, what are these things, and then we'll directly delve into the machine learning aspect of it. Okay, I'll stop recording here, and I'll take your questions if you have any.